Yes, so it's our pleasure today to have Joseph Jaeger. He's a professor at Georgia Tech, and he's going to talk today about his work with Nirvan Tyagi on how to handle adaptive compromise for practical encryption schemes. Thank you so much, Joseph, for giving the talk.
Thank you for hosting me. And as you mentioned, I'll be talking about my paper on handling adaptive compromise, which is joint work with Nirvan. Now, I want to, kind of set the stage for this by saying that this is, in some senses, not your standard sort of paper you've been hearing about in this seminar. I've, scrolled through the schedule a bit and looked at the papers you saw. And most of them are, they're about encrypted search, and they're kind of about new definitions for what encrypted search should do, or new constructions for existing definitions, maybe lower bounds for how efficient encrypted search can be. My paper comes from a kind of slightly different direction, let's say, where what I do in my work is provide new definitions for the kind of underlying primitives, think like encryption and PRFs, with the goal of allowing easier and more precise proofs about encrypted search or other applications. I like to think of my work as sort of about a kind of like meta-cryptography, in that it's not directly about applications, but instead about building the kind of formal tools that allow us to more easily analyze these other applications. And as part of this, in today's talk, I'll have various kind of philosophizing tangents about how to write definitions and proofs and how to think about them. To start off, whoops, my animations are slightly off, but that's fine. Talk about the setting of searchable symmetric encryption, which was kind of one of the main applications of my work. I guess to give a little historical background, I first had the gem of the idea behind my paper reading one other paper that was completely unrelated to searchable encryption, but then wasn't going to do anything with it because it was just motivated by this one paper. And only later did I kind of make the connection to searchable encryption and realize, oh, this thing I'm thinking about will be kind of much more broadly useful. So anyway, what's the setting for searchable encryption? We think about there being a database of documents. Each of these documents is associated with an identifier and a kind of bag of keywords associated with that document. And the goal is we want to be able to search for documents using the keywords that are associated with them. We want to do this in an encrypted way, so we can have a kind of honest user has their own secret key K, and they offload to some server an encryption of their database. They want to be able to search for all of the documents associated with a particular keyword. To do this, they process the keyword using their key to generate some token specific for that keyword, give it to the database, and then the server does some sort of computation and should be able to send back the encrypted documents containing that keyword. Informally speaking, our goal here is to hide as much as possible about the database and the searches that the honest user are doing. But for efficiency purposes, we're going to allow some measure of leakage about what these queries are. And to kind of motivate my work, we'll talk about a particular scheme from my actually very first paper I ever wrote while I was an undergrad. And I choose this one both because I'm familiar with it and because I think it's a kind of maybe one of the simplest schemes that kind of really gets at the heart of what motivated my work. So in the scheme, pi sub basic, we're going to think of the user as having a kind of different keyword, different keys for each keyword, one key for encryption, one key using for PRF. Kind of under the hood, think of these keys as being produced from a PRF using the master secret key. Then how the encrypted database is going to work is that the encrypted database is going to have this huge table where the table maps random looking labels to random looking ciphertexts. And kind of under the hood, how these are produced is that for a particular keyword W, we iterate over all the different documents containing the keyword W. We apply a POF to a counter to get a label for the ith document, and then we encrypt that. We encrypt more particular the identifier of that document to get the ith ciphertext, and the ith label maps to the ith ciphertext. When I want to perform a search, the token I'm going to give to the server is just the 2 keys associated with the keyword that I'm searching on. This will allow the server to iterate over different values of I, reproducing the label, and then search in its table to see if it has a ciphertext for that label. If it has a ciphertext for that label, it decrypts the ciphertext to learn the identifier of the document it's supposed to return. And I'm not very focusing on it, but just think of the document as being kind of encrypted somewhere else associated with their identifiers. So now that we have this protocol, we have to think about kind of what exactly does our security notion look like. And I'm not going to be super formal here, but the kind of definition we use is a simulation-based definition, which goes back to this definition in I forget when the paper came out, maybe like early 2010s by Kurt Moeller, Gary Kamara, and Ostrovsky, that gave an adaptive simulation-based definition. In this definition, we consider the difference between 2 different worlds. In the real world, the attacker produces some database, and then it can make keyword queries to the database. When it makes a keyword query, it's given back the token associated with that keyword. In the ideal world, both the database and the tokens returned by these queries are produced by some simulator, which is given only leakage about the queries. In particular, the sort of leakage that the scheme I just showing has is that it leaks information about the size of the database. Think of kind of how many keyword document pairs there are and the sizes of the different documents, things like that. Whenever you make a search, it leaks all of the identifiers associated with the documents associated with that keyword. And it also leaks the search pattern, that if you make searches for the same keyword multiple times, we're able to identify the fact that yes, that was the same keyword being searched each time. So to try to write a proof of security for this game, we need to design a simulator, which is going to first kind of commit to the whole database, and then later be able to provide search tokens for it. This causes an issue for us because we're kind of committing to these outputs of the PRFs and encryptions before we know what the underlying identifiers or indices are. And then later, the search token are just keys for this PRF or encryption scheme that are supposed to kind of map those strings we already produced back to the actual result when someone makes a query. So we can think of this as the issue stemming from a kind of more general question of what I'm referring to the adaptive compromise setting. It's more broadly goes by lots of names: selective opening attacks, the commitment problem. There are a variety of names for this general sort of setting in cryptography. Broadly speaking, think of this as a setting where there's a number of parties that are communicating. An attacker is able to observe this communication, and then based on its observations, it adaptively compromises some set of the parties to learn their secret keys. This arises in many settings. What I just showed for searchable encryption is kind of sneakily exactly such a setting. We don't really think about it as compromising some user, but we can think of each keyword as roughly being associated to a user, and then we're adaptively choosing which keys associated to keywords that we want to see. And here's a number of primitives that has been studied for, and a number of different kind of definitional frameworks people have used for looking at different questions where this general problem arises. So in particular, the kind of core underlying tools that I'll be looking at my work is symmetric encryption and PRFs, which is part of why I started with that particular Pi basic scheme, because I need both symmetric encryption and PRS for that. And here we kind of very broadly are now interested in this simulation-based setting. It's like what I described before, that you're either interacting with a real protocol or you're interacting with some simulator given leakage about your queries. The advantage of an adversary is just the difference between the probabilities that it outputs one in these two different worlds. So if we think about symmetric encryption, the what's kind of underlying that Pi basic scheme we saw before is a definition where in the real world I can make encryption queries asking to get a particular message encrypted. And then I can also make exposure queries asking to be given the key that we use for encryption. The ideal world looks similar, but now the simulator is only given the lengths of the messages when you make encryption queries. And then later it's told the particular messages when you ask for a key to be exposed. Now you might kind of have in the back of your head, there's this thing called non-committing encryption, and non-committing encryption is what we're looking for here. The issue is that non-committing encryption needs long keys. Nielsen, back at Crypto 2002, showed that your key has to be as long as all of the messages that you'll ever encrypt, or this is unachievable unless we use programmable ideal models. This setting also kind of looks similar for PRFs. Now encryption is replaced with evaluation. And in the simulated world, to kind of really make it a PRF, the simulator doesn't get to pick the output for evaluation. Instead, the output for evaluation has to be a random string. And then later, the simulator is told all of the queries and the random strings returned and has to simulate a key that matches. Again, by essentially the same argument, this either needs long keys or we need to use programmable ideal models. And indeed, this approach of using programmable ideal models is a common approach that's been used many times that this setting appeared. One of the many papers in this list is the one that has the symmetric encryption, searchable symmetric encryption scheme I mentioned before. Kind of broadly speaking, though, the approach here is that we're going to fix a particular scheme and then prove security with respect to it in a programmable ideal model. Under the hood, what most of these SSE schemes were doing is they had a PRF, which they would model as a random oracle. And then when they needed to do encryption, they would do one of the kind of first encryption schemes you might see in a Crypto 101 class is you pick a random string, shove that through the PRF, and XOR it with the message to get your ciphertext. To simulate this scheme, it's fairly straightforward. You pick your ciphertext at random, and then later, when someone asks for a key to be exposed, you just pick a random key, and then you program this random oracle F to be consistent with the ciphertext you saw before. However, I want us to kind of take a step back and think some questions about, well, what if the PRF I want to use isn't modeled by a random oracle? Say it's a block cipher, which should be modeled by an ICO cipher. Or what if I didn't want to use this particular encryption scheme? What if I want to use a different mode of operation? Maybe I want to use GCM or something, or CBC. Following this status quo, what we would need to do is we would need to write a completely separate proof of security for each of these different choices we made, different modes of operations and different PRFs. So this is captured by this picture here, where for each mode of operation and each PRF, we have a separate proof for each application we want to write a proof for. Overall, that gives a cubic number of proofs. And it's kind of, cryptographer effort heavy. Moreover, each of these proofs is an ideal model programming proof, which while kind of conceptually straightforward is actually quite detail intensive and annoying to write thoroughly. To kind of exemplify this, let me categorize all of those papers I cited on the previous slide. Here in our categorization, what we want are proofs which are kind of fully detailed. They really lay out how every step works. And we don't want there to be bugs in our proofs, obviously. So the goal of a paper should be to be in this intersection of the Venn diagram. The fact that my intersection here is so small on the slide is a bit of a spoiler. When I looked at these papers, the majority of them did not have bugs, but they also just didn't work through the details of the kind of ideal model programming. Of all the examples I found that did try to work through the details, they all had a bug. Not a single one of them got the proof correct. And there were a couple extra schemes that both did not go through all the details, but did sketch a few details and made bugs in those few details they sketched. To be clear, I'm not trying to kind of like pick on these earlier papers. Indeed, separately, me and my co-author are both on 2 of these earlier papers. The difficulties that this shows in writing a thorough, correct proof indicates a need for a new approach. So here's that status quo again, where we have a cubic number of proofs, and each proof needs ideal model programming. The approach I use in my work instead looks like this. I introduce kind of target definitions for PRFs and for modes of operations. I'm able to show that various PRFs achieve my definition, that applying this definition of PRF into modes of operations gives CPA or CCA security. And then the high-level applications can be proven directly from my notions of CPA and CCA security, rather than having to delve into the details of the particular choice of encryption to get used. What this means is that there's only a linear number of proofs now in this graph, and that kind of complicated ideal model programming that led a number of books previously astray is relegated only to the lowest level of proofs, the proof of security for these PRFs. And once one person does them once, they don't need to be redone. So further works can kind of just inherit the ideal model programming without having to go through the details or just hand wave it away.
So sorry, Joseph, just one question. In your previous slide, when you mentioned like these, like in the Venn diagram about the bugs in the, yeah, this one. So is it, so for example, the NDSS paper or the Usenix paper that you pointed out, is it like, you mean bug in the proof, or is it like a bug on some instantiations that they picked? For example, like, can you tell us a little bit more?
So it's a bug in the proof. I'm not claiming that there's anything wrong with the actual schemes, or that they're insecure, or that there are any issues with any instantiation. It's just in the like formal proof there are issues. I'll talk about this a bit more later, but also at a high level, it's like not even that interesting of a bug from my perspective. Once I kind of point the bug out to you, it's relatively easy to just go, oh, okay, I missed a birthday bound term, but it's a birthday bound, we're fine. So the point is, some sense, not about the particulars of the bugs, but instead kind of what they say about how we write proofs. And maybe it's an indication that there are other bugs to be found in here that could potentially be more serious.
Thank you.
Right, so let me give just kind of like high level of what the different results in my paper. First, as I've already noted, I give different security definitions for encryption and PRFs in this adaptive compromise setting. Excuse me, I give example applications of this. And then I kind of lift results to show that known results you expect with our normal definitions for PRFs and encryption schemes kind of hold with my new definition. So, for example, CPA security plus ciphertext security still implies CCA security. Encrypt and MAC is still CCA secure. Random oracles and ideal ciphers are indeed good PRFs, and various standard modes of encryption do meet my CPA notion. This last one is part of a kind of general result about any mode of operation that's extractable, which is a somewhat technical property that I give just for basically capturing exactly what you need to write the proof. Right. So let me start kind of delving a bit more into what these security definitions look like. They can be viewed as existing in the same sort of simulation-based setting we saw before. And it looks very similar to pictures I gave before with a little bit nuance. Now it's a multi-user definition, where in the real world, I can ask user U to encrypt message M. I can ask an expose oracle to give me user U's key. And I also, make ideal primitives a kind of first-class object list. I'm very explicit about including ideal primitives as part of the game because the ideal primitive is the only reason this is achievable in the first place. The definition just doesn't make sense without ideal primitives. Then the ideal world is similar again. The simulator tries to simulate encryptions given the length of the messages. When it's asked to do an exposure, it's told what the underlying messages were. And crucially, the simulator is allowed to control the output of the ideal primitive. To get different variations of this, CCA security, you just add a decryption oracle. In the ideal world, the simulator is given the ciphertext that was queried and asked to decrypt it. There we go. You can also give various notions of, rather than CPA, you might want like indistinguishability from random, or you might want notions of key privacy, or you might want authenticated encryption. All these different variations of security that you're used to from normal indistinguishability-based definitions, you can get by just restricting the behavior of the simulator. And finally, the PRF definition is again just kind of replacing encryption with evaluation and requiring and kind of hard coding that the output of evaluation in the ideal world are completely random strings. Now here I want to kind of pause and give some of my meta philosophizing about definitions, and that it's important to think about the fact that kind of definitions serve dual purposes. Revisiting my picture from earlier, my CPA definition here. First, we want to be able to use it to prove the security of higher level applications. And we also want to be able to prove that kind of our various constructions achieve this notion. And you should really think about definitions when you're coming up with them as not being something that you just write down and use, but more it's a kind of process where you write down your definitions and then you start trying to write proofs with your definitions and seeing if you can write the proofs you want. And not just if you can write the proofs you want, but like how easy is it to write the proofs you want? And so in my paper, I spent a lot of work kind of making different tweaks in my definitions to try to make it as easy to use these definitions as possible. There's some inherent tension here, and that often parts of the proof, tweaks you can make to the proof for making it easier to prove higher level applications make it slightly more annoying to prove the security, to prove that something meets your security notion, or vice versa. So to talk about that concretely, just for a moment, here's the actual pseudocode for my CPA-based game and my PRF game. Let me see if I can get my pointer up. Okay, here's my pointer. So looking at the CPA game over here, we have, like I said before, an encryption oracle. In the encryption oracle, you're either getting the real encryptions when the bit is 1, or you're getting simulations by a simulator when the bit is 0. One kind of decision that I had to make here, which gives a trade-off between is it easier to prove results, prove schemes meet this, or to use it in higher level applications, is the fact that I let you keep querying this encryption oracle after you've already exposed a user. And then there just needs to be this little bit of a tweak that if you haven't exposed the user yet, the simulator is only given the length of the message. If the user has been exposed already, they're given the whole message. And here we have our exposure oracle, which gives back either the user's real key or a simulation of it. And here another like small tweak I made in the definition for the purposes of making it easier to use is that I give the simulator not just the different messages that were queried to encryption for that user, but I also give it the ciphertexts that were queried for that user. You could kind of, without loss of generality, not do this because the simulator can just store those ciphertexts itself. It can just remember what ciphertext is output. But doing it this way just kind of makes things easier for the simulator. In terms of when I'm actually writing proofs and trying to write down the simulator, I don't have to add that in every time. It's just given to me. And one of the small insignificant detail that I like to highlight is I quite like this notation for the simulator state that I kind of put the simulator state after the colon, and I treat that as being passed by reference rather than passed by value. It's a nice way to make it super explicit that the simulator is allowed to store state, and it kind of makes notation easier to have it passed by reference. Anyway, we can go through similar points with all the other definitions, but I won't bore you with that. I just wanted to highlight that there's kind of a lot of massaging that can go into a definition and trying to make it easier to use for the cryptographer afterwards.
I have a question.
Sure.
Do you mind going over the primitive bit again in the definition?
Sure. And I guess one thing I will mention quickly is that I have some ideas to do it slightly differently that make composition stuff nicer. I might get to it at the end of this talk, but probably not due to time. If you ever think about using my definitions, reach out to me and I'll show you the new version I'm working on. But as it is, the primitive here is supposed to model like your random oracle or your ideal cipher. And to kind of abstractly capture any sort of ideal model you might want, which might also be like your random oracle and an ideal cipher or multiple ideal ciphers or whatever. I just kind of abstractly capture it as some stateful algorithm that, given a message X, outputs a message Y. Behind the scenes, we kind of want there to be two versions of this algorithm. One version where you pick all of the state ahead of time. So think of like for a random oracle, I just pick the entire table ahead of time. And then another version where you lazily sample this object. Originally, I didn't have this requirement about their kind of being two versions that it works, but it leads to some very hairy technical details if there's some chance that the ideal primitive might give inconsistent queries across different queries. And then in terms of our security notion, how it's working is that in the real world, the output of the primitive oracle is produced by the actual ideal object, whatever it might be. And in the simulated world, the simulator just has complete control of the output of that oracle.
All right, thank you.
Okay. So as I mentioned earlier, in our paper, we used our definition to prove the security of several example applications. For searchable encryption, we considered the kind of basic searchable encryption scheme I showed earlier. The original paper by Cash et al. Provided a thorough proof in the non-adaptive setting. And for the adaptive setting, chose a particular random oracle-based scheme, which is basically treating the PRF as a random oracle and treating the using that simple encryption scheme I showed earlier from a random oracle. And then we gave a very short, just kind of sketch of the proof, not actually going into the details. In our work, we were able to reprove this result, now using our key private encryption definition and our security definition for PRFs, which both made the proof much easier to write and makes it more modular, because you can kind of after the fact choose which particular encryption scheme or which particular PRF you want to use. Next, we looked at work by Jaeger et al., which is my co-author, on self-revocable encryption. The idea with self-revocable encryption is inspired by like border searches. I want to encrypt data on my phone, and if I'm going to go through a border where I think the border agents might search through my phone, I have the ability to intentionally revoke my own ability to access the data that I have on my phone and then gain it back later. For this proof, they introduced something called the ideal encryption model, which is a new and very strong ideal model they introduced and isn't achieved by standard schemes like GCM in terms of indifferentiability. And moreover, the proof had a very subtle bug in it. Again, we were able to give a new proof of security for this in our work using our CPA definition. And finally, with the kind of ePrint version of the opaque paper, introduced the notion that they called equivocal encryption, which is basically a single user, single challenge version of my definition. And so I show that my CPA definition implies the equivocal encryption definition. And moreover, as a result, we kind of make rigorous their claims that most encryption schemes would be able to satisfy their equivocal encryption definition. Right, so next I want to go into a bit of a kind of philosophical side about how we should interpret the results of our paper, because it's actually quite subtle in these weird ways. So first, to start off, let's think about the kind of traditional way that we think about ideal model analysis. Here we have, as cryptographers, have some scheme pi in mind, and we want to understand if it meets some security notion X when we're using, say, our favorite SHA-hash function. However, we run into an issue and we're unable to come up with any reasonable standard model assumption about SHA, which suffices to imply the security of pi. So instead, we kind of lift ourselves up to the random oracle model, replace SHA with a random oracle, and show that this scheme is secure when using a random oracle. Then we heuristically assume that when we actually instantiate this with SHA, security will still be maintained. If we try to kind of apply this framework for our definitions, say, think of X being my SIM AC CPA definition, we run into problems, which is those techniques of Nielsen I mentioned earlier readily apply to rule out the possibility of any standard model assumption achieving our notion. It just doesn't make sense in the standard model. Well, okay, you might think, what if we think of it like this? We'll start with our standard model proof that we achieve, our ideal model proof that we achieve SIM AC CPA security. And then we'll still thinking in the random oracle model, prove that some higher level protocol, pi prime, using pi as a underlying box, achieves the security notion Y. Then we can at least use our proof as a kind of stepping stone, heuristically assuming that pi prime achieves its desired security notion Y. unfortunately, again, we run into issues that, at least for the particular examples I considered, Nielsen's proof counterexample applies again. This leaves us with a bit of a conundrum, kind of what's the point of any of the results in my paper if we know that the standard model can't achieve the definitions that I've written. And so for that, I want to give you a kind of slightly different way to think about this. So here, our kind of X's and our Y's, they're really these incredibly strong definitions. And my view is that we want to think of there as being some kind of weakened analogous definitions, X prime and Y prime, which we may or may not know what X prime and Y prime should be, but we just think of there being such definitions. And then because of the strength of X and Y, we can, in the random oracle, see that X implies X prime, Y implies Y prime. And then, hopefully, this kind of X prime and Y prime are definitions that actually can be achieved in the standard model. And this allows us to heuristically assume that when we place the random oracle with your favorite SHA, you achieve this definition. To kind of make it concrete in the case of SSE that we talked about before, think about pi as being your PRF, and technically this should also be the encryption scheme, but whatever, pi is your PRF, X is my notion of SIM-AC PRF security. Then pi prime is the searchable encryption scheme. Y is the adaptive semantic security definition that we asked of the searchable encryption scheme. Okay. Now the question is, what should Y prime be? I don't 100% have an answer here, but one at least first thing to think about is adaptive indistinguishability-based security. In fact, if we go back to the kind of original SSE paper that gave the modern adaptive semantic security definitions that get used everywhere, they actually gave both semantic security definitions and an indistinguishability-based definition, where basically you provide two databases, and then you make search queries on the databases, and you're restricted to the case that the leakage between these two worlds has to be consistent. And so then you're just trying to distinguish between which database is actually being used. In their paper, they showed that semantic security implies indistinguishability. And I think motivated by that, basically all the following work has been using this semantic security definition. However, for a number of the papers that, a number of the protocols that have been designed, we know that they can't in the standard model achieve the semantic security definition because you run into these commitment issues. And this kind of leaves a very interesting question in my head that I don't even have a good idea of how I would tackle it all, but would like to encourage people to think about is the adaptive semantic security, oh, I wrote this backwards on my slide. It should be, is the indistinguishability-based definition actually meaningfully weaker than the semantic security-based definition? Is there some attack that could happen in the real world? Or is this just some sort of artifact of our definitions? On the other side, if it is actually weaker, is there some other intermediary notion between the two, which would be achievable potentially by these schemes in the standard model, so that we could think of that as being the kind of point of all this analysis? Then the value of doing the analysis, at least in the simulation-based definition in the random oracle model, is that we hope that whatever kind of intermediary definitions you might write down, they should in the random oracle model be implied by the definitions we're currently using, which would then allow you to kind of follow this flow of reasoning that I've been showing in my slides. Anyway, getting back to summarizing some of the results of my work, I showed that random oracles and ideal ciphers are SIM-AC PRF secure. This is a conceptually straightforward proof, yet quite detail intensive. Your simulation strategy is what you would naturally expect, which is Your evaluation queries give random responses. On a key exposure, you just pick a random key, and then you program the ideal model to be consistent with what you picked. The core of the analysis boils down to ruling out some bad events where the attacker could notice your programming. The possible bad events are that multiple users sample the same key. The attacker queries the ideal primitive on one of the user's keys before it was exposed, meaning before this key was even picked, or in the ideal cipher model, if the random responses happen to be inconsistent with it being a permutation. This first bug I pointed out, or this first bad event I pointed out, is the source of almost all of the proof bugs from that slide I showed earlier. I think all but one, maybe. And so, like I said before, that's not that exciting of a bug. I point out the fact that the keys between users can collide, and you say, oh, okay, yeah, throw a birthday bound on, the proof goes through. And I mean, yeah, I agree. The point is that it's not about the particulars of the bug. It's instead about kind of the incentives of how we write proofs and the culture surrounding it. The fact that proofs aren't reviewed thoroughly, proofs aren't kind of written thoroughly to go through all the details, but there are reasons that this is the case. It's hard to write these proofs thoroughly, and it's quite tedious, particularly when we get to like this ideal model reprogramming, which, like I said, is conceptually simple, but technically quite detailed to write down. But you know, it's I think as a culture, it's also really important that we want to kind of push ourselves to write proofs as well as we can and to review them as well as we can, because at the end of the day, we're trying to build systems which get deployed and, you know, are being used to protect really important data.
So Joseph, just I have a question about the 3 bullets that you had in the previous slide. Like when you say multiple users, can you elaborate on that a little bit? Because, like, for example, in the case of PyBasic, like, so do you mean users like the different users that they use the same scheme, or do you mean like every user sample its own key and use PyBase? So can you clarify what do you mean by multiple users here?
Right. So first, just ignoring PyBasic for a second, just talking about my SIMAC PRF definition. My SIMAC PRF definition is a multi-user definition where each user has their own PRF key, and you can kind of query them independently. So I'm talking about the collisions between their PRF keys. And then how this kind of lifts up to PyBasic is not that I'm thinking about them being multi-users there, but kind of under the hood, what happens is when I write my proof, each different keyword acts as a different user because each different keyword has its own PRF key associated with it. So, so when I kind of plug this analysis together with the PyBasic analysis, the multi-users sampling the same key would correspond to there being multiple keywords that had the same PRF key associated with them. If that's the case, you'll also have issues with correctness in this game. But
yeah, I see. Makes sense. Thank you.
Right. Yeah. What else do I want to say? So part of how I think about the kind of placement of my current work is that making proofs easier to write will encourage people to write better proofs, both in terms of being more thorough and more easily checkable, which encourages people to check them potentially. And you know, part of my own philosophy about how I write proofs for myself is that I really strive to make it so that my proofs are precise enough that bugs can be found and concretely pointed out. There's one issue you run into. Yeah, I did have this slide next. If we kind of look back at this slide, I really want to kind of highlight that while it might feel like the ones that have bugs in them are the ones that kind of did the worst job, to phrase it oddly. From my perspective, like those are the ones that I'm the happiest with. They at least tried to go through all the details, which means as someone reviewing the proof, if I read it closely and there's some issue, their scheme's actually insecure, I have kind of the highest chances of being able to identify where it's insecure and being able to point at a specific place and say, here's where the proof bug happened. Here's an attack showing it or something like that. Whereas there can be this issue that someone might have a proof which is just kind of not detailed enough to really say if it's right or wrong. In terms of kind of how I wrote my own proofs, here's the simulator that I gave for PyBasic. It's kind of super explicitly written out. The fact that I'm using simulators for the underlying PRF and the underlying CPA greatly simplifies the code of this as compared to if I had to do the random oracle programming inside of this for a particular encryption scheme and a particular PRF. And then I very explicitly give a sequence of hybrids, adversaries that show you can't distinguish between hybrids, and then more hybrids, and then more adversaries until we get to the end.
Joseph, sorry, I have a question. Maybe you already talked about it, but maybe I missed it. So do we know any sort of equivalence between, let's say, CPA security and these new definitions that you're proposing? Or let's say if we have some encryption scheme which we know to be, CPA or CCA secure, do we need to prove that they also satisfy your definitions?
Sure. My definitions imply the kind of normal indistinguishability based versions of them for all the different variants. The other implication doesn't hold, unsurprisingly, because by definition they're impossible in the standard model. And in terms of the proof, this is something that I kind of worked on a lot and have a little bit of a result towards in my paper, which is that informally speaking, any scheme you've seen before that satisfies CPA will also achieve my CPA. But I can't generically do some sort of lifting result because there are you can play tricks by just shoving one-way permutations in places that make it so that it doesn't achieve my definition. But that doesn't happen with schemes that people use in practice. And in particular, for CPA security, I introduced this notion of extractability and say that if your scheme achieves extractability and it's indistinguishable from random ciphertext secure, then it is also SIM-AC indistinguishable from ciphertext secure. And this was a somewhat not super formal point, but I kind of pointed out the fact that underlying the kind of typical way you write a proof that something achieves in $ security, underlying that is exactly the analysis that I need for proving that you achieve extractability. So I got as close as I could to making it automatic, but I couldn't make it automatic.
Yeah, thank you.
Not going to go into detail here, but I just wanted to point that I have a tendency to write these huge games and proofs, which takes a lot of work, but it has worked out for me. This is a completely unrelated previous paper where I had these huge pseudocode-based proofs and made my proof very explicit. And I found a bug in my own proof and had to fix it. What do we have time? Okay, I'll quickly run through the rest. There's nice lifting results that CPA plus ciphertext still gives you CCA. The simulator just returns bot for the decryption queries. Encrypt in Mac is still secure. Encrypt in Mac is still secure. And that typical modes of operation based on an underlying PRF will meet my notion. And this is where we're getting into what you were just asking about, that A typical result will show that if the underlying PRF is secure, then I achieve indistinguishability from random ciphertext. My goal is to do the same with the SIM-AC versions of these definitions. I forget what I was saying with that picture, but to walk through a kind of picture here of that very simple scheme we saw before. How do you simulate? You pick the ciphertext at random, and then when someone asks for an exposure, you just have to kind of look at the ciphertext, look at the message, and infer what the outputs of the PRF were that caused this message to happen. And that inferring of what the outputs of the PRF are is what I'm calling this extraction. And that if a scheme is extractable, meaning that you can do this extraction, then I achieve security. Extractability has kind of three parts about it. When you extract from a ciphertext and then re-encrypt, you actually get back the ciphertext. The extracted output to the PRF have to look random if the ciphertext was picked at random. And you're unlikely to cause inconsistencies in the PRF by doing this extraction. The correctness and uniformity are straightforward. The security part is typically implicit in the existing security proofs for these schemes. Anyway, I think it's right at 12. And here's just summarizing again the different contributions in my paper. And I'm happy to take any further questions.
Yeah, thank you, Joseph. It was great. Like, yeah, Yassini has a question.
Yeah, thanks for the talk. At the end, you mentioned this question about whether the simulation-based definition is meaningfully stronger than the game-based definition, and whether there's something, and if so, whether there's something in the middle. And I guess, but like, there's another reason why the simulation-based definition may be more useful, besides just implying the game-based definition and the game-based definition not implying the simulation-based definition, is that, and this is not a formal statement, this is just intuition, is that the simulation-based definition may have better composability guarantees. And so, you know, that would be a reason why we may want to stick with the simulation-based definition. Now, it is possible that maybe like this intermediate definition, like whatever that is, maybe also has good composability guarantees. But just wanted to point out that's another consideration, you know, that does, or that may matter.
Sure. I guess I'll quickly say that, yes, I agree. Maybe I'll quickly mention that my own definitions have a little bit of composability annoyance, which is kind of, well, maybe I won't show the slide, but with my own definitions, I completely replace the ideal object with a simulator when I use it inside my proof, which then means that it's really difficult to use the same ideal object multiple places, even if kind of conceptually you should be able to. So for example, inside of PyBasic, if I use a random oracle as my PRF, and I use that same random oracle inside of my encryption scheme to build my encryption scheme, conceptually, there should be no issue with that. But with my current definitions, there's just absolutely no way to prove it, because once you do your first reduction, you'll have replaced that random oracle. And so that's where I was hinting at, that I have kind of future work I'm looking on, slightly tweaking the definition, which is the definition on this slide. And the kind of important difference now is that I need ideal objects to have some explicit notion of being programmable. And then rather than the simulator having complete control of the ideal object, they're just given oracle access to be allowed to program it. And the attacker also is given the ability to program the ideal object, which is super weird, but it's what I need to make these definitions do this sort of compositions where I could reuse the same ideal object multiple places. For random oracles, it's not really that big of a deal because I could just create multiple random oracles by doing domain separation. But for something like an ideal cipher, it's much less clear to me how I could create multiple ideal ciphers, which is why I want this kind of composability. Anyway, that was that. Happy to take any more questions.
So thank you, Joseph, for the talk. It was very interesting, and looking forward to your next works. Yeah, thank you.
Thank you.
Bye.